Okay. Let's see here. Alrighty, so hopefully you enjoyed the Sphinx cat while we were waiting on other guests, and we can put this out of the way for now.
My daughter said, "What the hell is that?"
Yeah, they're slightly more hypoallergenic, but not necessarily. Yeah, they're kind of terrifying. They're quite terrifying. So, well, you know, scaring people is what I do. That's how it rolls. Okay. All right, so we've got a continuation of the ADT bag. I believe we had needed to discuss the linked implementation, and also we need to talk about efficiency of algorithms. Okay, so I will at least open that up as well. Okay, and let me get the slides. Let's look at that again. What chapters was it? Oh, it's yeah, 1 through 3. So I think 3 is where we should be picking up on. Okay, yeah, we did a basic overview of what a link chain would entail, but we'll do a little bit more review and then go for the rest of the slides, and then we'll talk about Big O notation. All right, are there any questions about previous material or anything before we start? Nope. Okay. So as I had noted, I'm going to back up just a slight bit here, but as I'd noted there, the forming the chain involves an individual. In this case, we call it the instructor. It's going to be a variable in our linked bag class, but we'll look at it as an instructor right now. And all they have to remember is the number on the back of the desk. They don't have to remember, you know, and they don't have to remember or set up everything in the classroom so that everything's right in front of them like we do with an array. We could be wasting desks because people haven't arrived yet. But here, as the people arrive, the idea is that they're bringing a desk with them and setting it down. Obviously, this is all analogous. It isn't identical to what actually happens, but it gives us maybe a better idea. So this guy is basically referencing that first desk in the chain. And at this point, it's the only desk. When a new person comes in, the instructor has to rememorize what number, but then that desk, before he does the rememorization, whoever's at that desk writes on their desk the number that the instructor did have written down because it was pointing to the previous first desk in the list. And now this new desk is the first desk, so that the instructor has to remember that number, and then that desk number is pointing to the next desk. I'm sorry, the number on the desk top is pointing to the number of the next desk that used to be the first. Okay, so this one used to be the first, but it no longer is because this one took its place. So we're adding to the front of this chain of desks is the idea. Okay, so another one arrives, so a third one arrives, and what happens is that now the desk number 4 is no longer going to be the front of the list or the head of the list. We'll notice before it was, and the instructor had that number memorized, but this new desk in town memorizes by putting on its desktop what the instructor was previously memorizing, i.e. the address of the previous front desk on its desktop. And then the instructor memorizes now the number on the back of this desk, and then they create a chain in this way. So 20 just has to remember one other desk, and then the 4, when it gets to there, the 4 has to remember one other desk. So they can keep track of what order the desks came in, okay? Or the people came in and sat at the desks. So right here we have, again, the process. For the first student, we have a new desk representing the new student's desk. New student sits at the desk, so that's the data, essentially. The instructor memorizes the address of that desk, okay? As other students arrive, the new desk represents the new student's desk. The new student sits at the desk, so that's putting the data in the node, essentially. But that node, or that desk, in this case, is not yet really part of the chain. But what we have to do is first write the instructor's memorized address on the new desk, because we don't want to lose track of whatever previous desks came in. And then the instructor has to memorize just the address of the new desk, so we don't lose the entire chain. Okay, so here is what the node looks like, again in code. We have the 2 pieces of data that we're interested in. We have the private T data, and then I'm saying both are data because they're both fields. So private T data is the actual data we're interested in tracking, like the data that we would be putting in these cells of an array if we had an array. And then private node next is so we don't lose the rest of this chain, okay? The constructor that's doing all the work in this case is this one. So we have data equals data portion and next equals next node. They did choose to change the names here. It's whatever. In this case, it's at least a good pick of names, but I would just put this.data equals data and just pass them in as data and next. But this is how the node works. And if you just call the constructor with just the data portion, it will automatically call the other constructor and set next node to null. So that's something that you can do as well. So right here, this is just 2 nodes that reference, or that each reference data. The nodes in this chain, we can see that the first node here has its own data it's referencing. This is an address, and so is this, but this is an address to whatever the data type is of the data that we're tracking. And this one also looks at its data. If we didn't have this arrow here, meaning the data, or the address under next to point to the next node in the chain, we would lose the rest of the chain. So we have to connect them, all right? It's like having a bunch of chain links, but not actually linking them together, unless you have this next thing here. Okay, so how does this code, or what does this code look like when we actually bring it into reality? We have this linked bag right here that implements the bag interface, private node first node, and private int number of entries right here. The linked bag sets the first node to null, number of entries to 0. So that's how we'd expect the bag to start. Remember, the bag and the node are 2 separate classes. The bag represents the overall data structure. A node just represents its own little world with its single data of whatever type we're managing, and also a reference to the next node in the chain, right? So this starts with this where we just set first node equal to null because we have no nodes in our chain yet, and number of entries is clearly 0 because there's no nodes in our chain yet. So in this technique, they're using a private inner class. So they have this public outer class called linked bag, but inside they're doing a private inner class that they're naming node. And then they show you the data over on the other slide with the node data. So what happens here is, again, this bag has to hold an address, a single address, which it declares up here called first node. And this linked bag is kind of acting like the instructor. The instructor just has to memorize using its using a first node pointer or first student or whatever you'd want to think of it as, to point to the first desk in the chain or the first node in the chain. Down here, an empty chain, and then a new, let's say a new node just gets created, right? We haven't really put together how does this work yet, but let's say a new node gets created. We have temporarily a variable called new node that has created this object on the heap. So on the free store or the heap, which is the area where dynamic memory is created, we have this node, and it has a data portion and it has a next portion. It's a brand new node, so its next portion actually has its next point to null, so it is not actually pointing to another object, and its data portion, its data field, is pointing to whatever the new entry was. So that's great. We have this new node here, but if we, let's say this was all done in a method here, as soon as that method's done, like add data or whatever, or add node, this whole thing's going to die. This node's going to be not have anything pointing to it anymore because new node and new entry will go out of scope. So how do we actually keep it from doing that? Well, we have to have a variable that has a longer lifetime than just the lifetime of a variable inside of a method. We need a variable that, for example, lives at the class level, okay? Right, so first node, that's a good option. So that will live as long as the linked bag object lives when we create a linked bag object. And we'll use first node to do that. So we have first node equal whatever new node is currently pointing to, meaning it'll copy the memory address. So now it's pointing to this node in the chain, right? So now it's part of the actual chain. So when these two variables die after when new node and new entry themselves die and can no longer point to this object, there will still be something pointing to it, so it won't get garbage collected. So now we have first node and then some arbitrary number of nodes here. What happens when we insert a brand new node and we've already got some nodes? Okay, so we're really only concerned at what happens right at the front. It doesn't matter if there's 1 or 700 million nodes after this one. The reality is going to be the same as far as how we insert the node. So right here, we have the initial list that we started with, and we just created a brand new node here. And then how do we actually splice this node in so that first node points to it? Well, you have to be careful because the order matters. If I immediately say, oh, first node, I'm going to point to the new node. If it does that, just like a child letting go of a string on a balloon, this thing's going to go flying off into, the ether. This first node actually, if we point to new node with this variable, this actual object here will no longer have anything pointing to it. So it's going to get garbage collected, and then whatever it's pointing to will get garbage collected, and then whatever it's pointing to will get garbage collected all the way down the list. So we're basically leaving a trail of destruction in our wake here. So we can't just immediately point first node to this new node. We have to find a way to, because we're interested in holding whatever data this thing does. We want to hold the data, that's our key. But we also don't want to lose the rest of the list, or the rest of the bag in this case, the chain. So what do? Well, this new node has to first point to whatever first node's pointing to. So its next, instead of being null, will point to whatever first node is pointing to. And then first node can then change, can update what it's pointing to the new node. That's exactly what's going on over here in part B. If we need numbers on these things, we would say that this happens first, and then first node can break its link with the previous first node up here and point to the new first node down here. Okay, so we're adding nodes near the front. Every time a new one comes in, we set its data, have it point its next to the current first node, and then now the first node variable points to that new node in memory because it just became the first node in the chain. Okay. We have all kinds of other variables and methods that we're going to be dealing with. So adding, this is kind of what we just said we were doing. New node equals new node with an entry. So whatever data we're trying to hold, we want to do that. You'll remember the constructors for node, the one that doesn't have a second argument passed to it, just sets that to null. So that means this node is just setting out all on its own not part of the chain yet. And then we set next new node to new nodes next equal to first node. Okay. We could actually pass first node as the second argument here, to be honest. And then you set first node equal to new node. Okay, that's what actually pulls it into the official chain. This move right here, the new node next equals first node, that says make new node reference the rest of the chain. So basically, new nodes next points to the current first node, so we don't lose the rest of the chain when first node variable gets updated. Because remember, this might look a little confusing because you're like, wait a minute, I pointed to first node, and then first node changed what it is, and I don't understand that. Remember, this is where it's really important to distinguish between references and the objects they are referencing. Otherwise, understanding how all this pointing and addresses and all this stuff is working doesn't make any sense. It's kind of interesting because usually what we do when I say new node equals new node, this thing returns a memory address and the new node holds that memory address. So in one respect, the variable itself, this reference variable named new node of type node, is just holding an address, okay? But then we can start treating it like it's the actual object. So anytime you use the dot operator, you're actually kind of treating it like it's the actual object, even though that actual variable only holds an address. Java knows what we mean when we say new node dot next. It knows that the address itself doesn't hold any particular meaning. It's just ultimately an integer, a really large integer. It knows what we want to do is actually access the object. However, when you assign a value to any of these actual variables of reference types, it doesn't treat it like the object, it treats it like the address, okay? Or when you're assigning a value to it. So when I say new node dot next equals first node, I'm grabbing the address that first node has. So at this point, first node and new node dot next have the exact same address. Let's say it's FF2211. Now I have to update first node, which currently contains FF2211 to whatever new node is. Let's say it's 112233. So now after this line, first node will then contain 112233 and refer to the new node, which is the new head of the list or the first node of the list, rather than the one that was at FF1122. Okay. Then we return true, just saying that we were able to add it. So we haven't come up with any conditions where it would fail just yet. Okay. So to array, with the array-based implementation, we kind of just went cell by cell and copied the element over into a new array and returned it. So we have to kind of simulate something similar in this situation. So we create our array, just like we did in the array-based implementation. And then we have to walk the chain because we don't have random access to the array. That's one of the benefits of arrays themselves, is that we have this quality called random access. Random access means I can access different elements in the array whenever I want them, basically by just using an index. I can just say, oh yeah, hop to cell number 15, and it'll just immediately go there. Because it just does a little tiny, the system does a tiny bit of math, and it adds, oh, okay, so you're holding references, they're 8 bytes each, and you want to go to the 16th one. It's all contiguous memory, and I know where the first one starts. I just add that to the address of the first one, and it jumps all the way to the address of the, the one at the 17th one, okay, at address 16. So it can do that. That's a really good benefit of arrays. The problems we saw with arrays is that you have to move a bunch of stuff over to make room for new data in some cases, or close gaps and things like that. Sometimes you end up moving data, and sometimes it's not as efficient as we could possibly have it. So with this method, though, we can't use random access because the nodes are not guaranteed to be actually contiguous to each other. Okay, so if I bring Paint over here, oops, oh, we got the cat still. 1 second, I'm sorry, I'll bring the cat back later. Don't worry, I know you're all worried. Okay, so what we have here is this, a bunch of nodes out in memory. They are not contiguous. it would be very rare to actually, it would actually be kind of a, I wouldn't say a miracle, but it would be a rare occurrence for any of these to really be right next to each other. And in any case, even if we can't depend on every one of them to be right next to each other, we can't depend on using little mathematical tricks or expecting the system to be able to use little mathematical tricks to use indexing. Okay, so let's say the first node right here is pointing to that, okay, or contains the address of this node right here. This has some sort of data over here. This one points to that one, right? And then that one has data. That one points to maybe this one. That one has data. Maybe this one points to that one. We don't know, right? So they're all over the heap and they're all pointing to each other and it's just all over the place. So we cannot depend on random access. So the only thing we can do if we want to go, if we wanted to go to say the fourth element is we'd have to walk down to get to the fourth element. We'd have to start at the first one and say, hey, what's your next? Oh, it's this one. Oh, okay. Well, hey, what's your next? What's your next? What's your next? And then you go down until you got to the fourth one. That's exactly what we're doing here. So we grab the address of first node, which you can see right here, in a variable, a local variable called current node. And you can see that we also are counting indices. Okay, so we can actually use this with our array. So in index 0, we set index 0 equal to current node's data. So when you first go into the loop, current node data, that'll be the first node because we just set current node equal to first node. Now, there are two checks here going on here that both have to be true. The index has to be less than number of entries. That's just kind of a sanity check to ensure that we don't go outside the bounds of the array. That should be also the same as the current node not equal to null. So both of those should be fairly consistent, but both checks are in there just to be safe. So if I'm going through this and I do in fact have some nodes left, I can say result at 0 equals that current node's data. Then I increment the index. This is how we move on to the next node to see what it has. We say current node equals current node's next. So current node at the beginning was the first node in the chain. Now it's the second node after this line's executed. Goes back up to the top. Make sure this is set. If it would get to null, that means we're on the last node, so it would break out of the loop. Or if it would get to higher than the number of entries, up to the number of entries, we would know that it was outside the bounds. But we set result at index 1 now equal to current node's data, so the second node's data, increment index to 2, and then we set second node's address that it's referring to its next field. That means it's now pointing to the third node. And then it goes up again and it keeps doing this over and over and over again, depending on how many nodes you have in the chain. It doesn't matter if it's 100, 1,000, or 2, or 0. If you have nothing in the chain and you say 2 array, guess what's going to happen? It's not going to work. Okay, you're going to have the first node is going to be null. It's never going to even go into the loop because it'll say is null not equal to null? Well, that's false. And with an and, we can't have a false. So it'll break out and then return our sad empty array. So right here, this is a sample program that would test our hypothetical full implementation of the bag. We would print out creating an empty bag. They're using a bag interface reference. You could use the linked bag reference, but they're just showing you that it's flexible because they use the same thing for the array bag and it worked fine. And it'll do the same thing with the linked bag. So test is empty and display bag, they're just doing some tests here. They have a string array that they're using just to populate the bag. So test is empty. If I grab a bag and if the bag is empty, the parameter empty should be true. Otherwise it should be false. Okay, so if I expect it, this is definitely a testing method. This would be like part of, you could even create it as part of test-driven development. When you pass in the expected value over here, if they don't match, you can then say, okay, something's wrong. So in here, they're just going through not empty, but it is an error, empty, but it is not empty error. So if there's some sort of conflict here, meaning whoever called this expected it to be empty, but it's not, or expected it to be not empty, but it is, then your data structure has a problem. So this is, of course, not a method of the bag itself. This is just a tester method. Okay, this is a common testing technique. This is just something you could write in your own testing suite. You could use JUnit, which helps with tests, or you could just write it in here as one of the methods you call from main. It doesn't really matter, especially for smaller stuff. Okay, so what are other methods of our linked bag? So our linked bag, we have get frequency of. So we had that in the interface. We have to implement it because it was part of the interface, and we've agreed to do that. So what's our option, or what do we do? We set frequency to 0, loop counter to 0, and current node equal to first node. So again, we start at the beginning, and we still have this update at the bottom of the loop, current node equals current node's next. But what happens inside? So we're counting the loop itself because we don't want that to exceed the number of entries. Again, that's just another fail-safe. But how do we actually increment or count the number of different items? We're interested in the data, so we should be using the equals method. Now, how is the equals method defined? That depends on whatever type T is. If it's type string, the nice Java developers have already written it for us. If it's our rectangle class, if we want it to do something other than compare their addresses, we have to write it ourselves. So if it's any of our custom classes, it's very common, and I would probably do it all the time, except in very rare circumstances. You should always implement equals, because we want to make sure that we know how to compare two items of the same type, because someone else might end up using it in this kind of way right here. But let's assume equals tells us if these two, whatever these things are that are being passed in, are equal, whether it's rectangles or horses or narwhals or sphinx cats. So you increment the frequency only if an entry equals the current node's data. Okay, so an entry is the one we're testing on. We say, does that equal the current node's data? If it doesn't, we skip over this, and then we just keep going. We go to the next node, test that one, keep going, keep going, keep going. As soon as you get a hit, you increment frequency, but you still keep going until the loop should be done, until we're at the end of the chain. Once we've done that, we return the frequency. And then that tells us how many of a particular value we found in the list.
Can I ask a question?
Yes.
On the last slide, and even in the toArray method, where is number of entries coming from? Where
is number of entries?
Yeah, that variable.
Number of entries is okay. So that's slide 21. Let's go back a little bit. You see the add, whenever we add a new node, it increments this. This is actually one of the fields.
I do.
It's not a parameter or anything. It's actually a we'll go back to 21 in just a second, but you see how it's one of the field variables we created with LinkBag?
Yep, thank you.
Yeah. So those should be consistent. Like, for example, we shouldn't really need to put, the while loop, we shouldn't have to put both conditions because when the chain gets to the end, or if number of entry gets to, or if the value you're going up to is about to get to number of entries, both should break out of the loop. So it shouldn't really matter. But that's just for, I think, for extra robusticity to add it to the program to make sure it's a little more robust. But that's where the number of entries is coming from, right? Okay, contains, this one's actually very similar to get frequency of. Oh, and by the way, I meant to mention it. I think I included it in some of the links I provided, didn't I? I did an ADT bag, and also, let's see here. What do we have here? Let me see here. What is it? Let's type link. Probably give it to me. Yeah, right here. Okay. So this right here, get share the link over there. Okay. I'm going to turn the sound off. Okay. So this right here is a supplement I did on linked chains, but the link is or should be on D2L. I don't know which. I'm trying to remember which thing it's under. That's only Zoom, isn't it? Let's let's find it real quick. Actually, I need to open this anyway. So.
Was that the inventory one where you add like Coke and bread?
I think so. Yeah, I believe so.
Okay.
Yes.
All right.
This is, I think that one. Let's make sure this is the, yeah, that's the Zoom version one. Okay. Yeah. So under content, I believe, I think even as far back, would it be here or maybe at week 2? No, week 2. This is just descriptive. Okay. So, yeah, week 2 probably has it under the learning guide. Yeah, right here. So practical example of using linked chains. This is kind of, I don't really talk about it in the context of the bag, but it's the same idea. We're creating a chain, and this that link very thoroughly explains like how does a chain work. Okay, so this is a a little longer description of just how to work with chains. So that could help you understand some of this if you're having any kind of trouble. But obviously it's a bare bones chain, but that might help you better before you move on or review some of the more complicated stuff like we're doing now. As long as you're getting kind of an overview idea of what's going on and you kind of understand what's going on, I would say you're in good position to maybe go back, review the link chain example that I posted, and then come back and it might make a little more sense what we're doing. And also how you have to also understand, what does a bag mean? What is a bag supposed to do? And we described that in the chapter 1 slides, and it's described in chapter 1 in the book as well. So contains is very similar to the get frequency of in some ways, because we have to go through and try to find where it is, but we're not counting this time. Notice we do have current node with get frequency of, but we have frequency, but in this case, what do we have? We only have Boolean found. And we set it to false initially because we assume, hey, it's not in there. And if we're proven wrong, like here, we set it to true. But you notice how we're controlling the loop. There's actually a couple different things controlling the loop. And this actually helps us get out of this loop faster than if we were to go through the whole chain, because we may not need to. What if it's the first node? We're not asked, is it the 5th one or is it the 12th one, or find me the last one. Excuse me. What we're asked here is just, does this list contain one of these things that I just passed in as an entry? And all you have to answer is yes or no. So as soon as I find one, it doesn't matter if it doesn't matter if every node, and there's 100 billion of them and they're all the same entry. It doesn't matter. All I have to do is find the first one. It's very different in that respect from get frequency of, which would have to count every single one. So this is how I detect it. So I assume it's found, or it's not found by false, or by default. And then I set current node equal to first node. And this loop says while not found. So you notice found is false. If I say not found, that's true. And for the while, the whole while condition to be true because of the and, both of its operands have to be true. So we know this one on this side will be true because it says not false. Now, if found is ever set to true, it'll then say not true, that's false. Therefore, the first operand of the and logical operator will be false, and therefore it won't even bother checking the second one, it'll just break out of the loop. But at our starting point here, before we've checked anything, we set found equal to false. So not found or not false is true. Excuse me. I'm getting over a bit of a cold. It's not COVID. I was tested twice, but it's kind of a nasty head cold I had over the weekend. So not found, and as long as we're not at the end of the list. Because remember, the node at the very beginning that we added to the list is going to point to null for its next. Because we're always setting the next of these nodes to first node. But guess what first node was at the very beginning, before we had any nodes in our list? First node was null. So that means it will contain the address null for its next. So as soon as we get to null for the current node, we'll know that we're done and we shouldn't try to access data. That would be dangerous to do so because null.data doesn't make any sense. Null isn't an object. Null is just an address. So this is kind of that situation where there is no object in existence. And when it isn't null, that means we do have an object, and therefore we can treat it like an object using the dot operator. We can say, hey, what's your data? And things like that. Or hey, what's your next? And that's exactly what we do here. So first time through, as long as it's not found and we're not at the end, if the entry does equal what we're looking for, we set found to true and skip over and then break out the loop, return true. Let's say that's not the case. Let's say found is false and we're at the first node, we're looping, but we always end up with this being false. So an entry does not end up equaling whatever the node's data is. So then what does it do in the else? Well, it just says go to the next node. Let's see if we get any luck there. It tests again, tests again, tests again, tests again. Let's say it never finds the data you're looking for. If that's the case, it'll get to here, right? It'll break out of the loop and it'll go down here. Now, what is found's value in that case? Found's value is false because it was never changed because we never found a match. So that's a really brilliant implementation. It's a very, very just consistent, simple, very straight to the point implementation. There's not a lot of frills or anything weird going on. It's very, very straightforward. So it'll remain false. We go through the whole thing. And then if this ends up breaking the loop, that means that didn't because it was never changed. So that means it just remained false. So we return false, right? So I guess what happens a lot of times, especially with regular users, whether it's kids playing video games or people using Zoom like we're using now, or people talking on a messenger program or playing Candy Crush Saga or texting or what have you, all of this stuff is not magical. There's some code underneath all of this, right? I have a list of the participants right now in front of me. I have let me say it again. It actually even says list participants. I have a list of participants, okay? There's a data structure called a list, okay? So I know somewhere in memory, there is either an array-based implementation or a link-based implementation. Holding each node, i.e. your names, right? All of your names and a bunch of functionality related to you on my, in memory on my computer. It's communicated over a network. There's some other complexities, but at the end of the day, something like this is probably going on. Okay, even if it's not something, even the developers of Zoom may not have had to deal with it because maybe the language developers did it for them. Like maybe if Zoom's, I'm not 100% sure what Zoom is programmed in, but let's assume C# or Java. They all have something like a list type data structure that they can work with. Okay, so it's actually very, very important that we know how to do this stuff, because you will probably find yourself using something like this or even identical to it. So how do we remove an item from a link chain? So we've spent all this time learning how to construct this sucker. How do we actually remove one? We have a couple problems. One is one major one that should pop up is how do we find the node to remove? And then the second one is how do we remove it without losing the rest of the chain, whatever's past it. Okay, so there are different cases for removing an item from a linked chain, and they're using desks again with the teacher's room analogy. So case one is your desk is the first in the chain of desks, and then case two just means the opposite of that. Your desk isn't the first in the chain of desks. Okay, that's basically what it says. So case one, how do we remove case one situation? So if you are the first desk, how do we remove you? Locate the first desk by asking the instructor for its address. Give the address written on the desk to the instructor, meaning it's going to be the actual address of the back of the second desk in the chain or node in the chain, and then return that desk for the hallway. So what does that look like? So it's currently looking at 14. And then what he what he does is he says, hey, 14, what do you have written on your desk? 14 says, oh, I have 20. So now he's going to remember 20, and he's going to basically jump over or skip memorizing this one. This one can then go out into the hallway. Okay. And it will be removed by janitorial staff. All right. So, and then this one points to the rest of the chain. So we didn't lose the chain in that situation. Well, what about case two? Case two, this is actually a really interesting option here. Now, one option would be to kind of, we've got node here, node there, node there, node there. Okay, and all these things are connected in some way, right? If we had to remove this one right here, I might say, okay, well, I want your, maybe tell it your next, is going to be null now, but first I have to set this next equal to that one. So I'm temporarily pointing to you. So now make your null next, or your next null. And then this one's no longer pointing to that. So we can erase that right there. And then this one's no longer pointing to that one. Okay, so it's pointing to null. So now this node is free. So we would have to walk down the chain and find it and then kind of splice out the node. We'd be pulling out the node. But the approach that they're looking at right now, what they're saying is, let's not focus on the node, let's focus on the data and then just redo, do what we did for the first desk, because it's actually easier. We don't have to really, do anything real complex. So move the student in the first desk to your former desk. So we don't want to lose. Remember, if case two says we aren't trying to remove the first desk, the student in the first desk, in other words, the data sitting at the first node, is not what we want to remove. So we're saying move the data to the desk that we're trying to remove, and then remove the first desk. Okay, so you're basically, in a real life scenario, you'd kind of be swapping the students and then having the student you're trying to remove to take the desk out into the hallway. In Java, you basically overwrite the value, no student to take out in the hallway, and then you remove the desk just like you did in case one. You use first node and you jump over. Okay. So this is what this looks like in a chain of nodes just prior to removing the first node. Okay, so this is case one. Case one says, oh, I'm pointing to this. Let's just say, okay, hey, first node, I want first node to now point to first node's next. So all this does is it jumps. That's what we see here. So this one's no longer part of the chain. It has no one pointing to it, so it will be garbage collected. All right, that's how we remove that. Here's a little helper method that we could use. This says it's method remove. That is not method remove, it's get reference to, but it's used to help the method remove. So I think they may or may not have intended this on this slide, but this is to help the method remove. Get reference to a particular piece of data. So what they did is they said, we're going to make it private because it's not part of the interface of the bag. Bag has no idea what get reference to means. It doesn't care. But we might want to use this in this particular implementation to walk the list to find a particular entry and then return the address of that entry so we can go straight to it. And if you get the address of that entry, you're pointing to, or you're holding the address of a particular object, and then you can just say, okay, that's the node I'm trying to remove. Now, if it goes through the whole thing and it ends up getting it null, then current node is going to be null, and you won't be able to, use it to try to point to another, or say, hey, we're going to remove this one or whatever. So what we do here is we set Boolean found equal to false, node current node equal to first node. This is nearly identical to the contains, right? This is essentially identical to the contains because we end up setting found to true. And the difference between this and contains is I don't return found, I return current node. So if it was found, it would skip over here and not go to the next node. It would go up here, break out of the loop, and then whatever current node stopped on, like it was playing musical chairs or hot potato, whatever it stopped on, is going to be the address of the node that we're trying to remove, because we found it. Okay, because whatever got us there and got us back up into the loop, we had a hit here, and that meant that whatever current node's address was, that's the one we're trying to get rid of. Okay, so we to do remove, we first get reference to an entry, and look, they're accommodating to make sure it's not null, because it could have been null, meaning I never found the entry. And if it didn't find the entry, the remove method returns false, indicating I couldn't remove that because it didn't exist. Okay. So what if it does exist? What if it is not null? This is the whole moving chairs thing. I set that node, right? The node that I want to remove, and I'm not actually removing the node, I'm getting rid of the data because we don't want to track that data anymore. So I'm overwriting the data at that node with the data of the first node. And then what do? I just say first node equals first node's next. So you remove the first node. This actually physically or digitally, I guess, removes the first node. So we've still preserved the data because we copied the current first node's data into this thing we don't care about anymore, or at least the data we didn't care about, but we leave the node intact. Now, what is this going to do? This is going to change the order, but does the bag say we have to keep the elements in the order that they were added? Is that a yes or a no?
That's a no.
That's a no. So the bag says it doesn't matter what order it is. Now, we'd have a different problem if we had like a list that says you have to keep these in the same order. But if you'll remember, we did something very similar with the array. You remember what we did with the array that was similar to this to avoid having to do a bunch of work? Anyone want to take a guess with the array-based implementation of this? Anyone? Tom?
Didn't we just move the piece that we wanted to the end?
Kinda. Yeah, I think you got it like slightly backwards. The item that we wanted to get rid of, we actually copied the end element over that item. Like, remember with the things with like Werner and Nancy or Vince and Nancy or whoever?
Oh yeah, it is. It's backwards from what I was thinking.
Yeah, it's okay. We removed the element at the end to the spot we're trying to just quote delete. So we didn't actually shift anything over. We saved ourselves a whole lot of time. Okay. And here it's kind of the same thing in some ways. We still have to find the data, but we don't have to do all this, like, let's point to the node and make sure that we don't lose it. And then let's, bypass it. And then let's remove that reference and all this other stuff. We're actually saving some time here too, but it's over the same situation. And we're using to our advantage the definition of the bag that says the order doesn't matter. And that's something you have to keep in mind when you make any kind of data structure or even data type. When you're developing these types of things, you always want to keep in mind, what are like programmatic advantages I can take, or things I can take advantage of that would not hurt the performance, might even help the performance, right? And won't change the result. Okay. So if this expected them to be in order and we just arbitrarily started moving stuff all around, this would give us logic errors all over the place, because we'd expect data to be in a certain order and we're getting it in a different order. So it's not the correct order. Okay, so that would be a logic error. But since it says, hey, it says nothing about order, we can violate the order. It doesn't matter. Okay, this one's pretty easy. Yes.
On the last, so even the last slide, the get reference to, that one was a private method. Why did they have that as, why did they want to restrict the client app from being able to get reference to?
Well, that's a really good question. There's a lot of developers think you should just, open up everything to the client. They should be able to do whatever. But remember, the client is accessing this through either through the bag interface, or as far as they're concerned, they only have a certain set of methods to deal with. And that was what we defined in the bag interface. Get reference to was not defined in the bag interface, right? Because it doesn't really help the client to directly grab the reference to any given item. We're doing it because it helps other methods determine where a particular thing is located. So we've decided to make it private. So basically you only give the client as much access as they need, but no more.
Yeah. All right. Thank you.
It helps preserve encapsulation, right? Because we're not damaging or allowing the client to access the internal workings. Even with whether it's the array-based implementation or the link-based implementation, you'll recall that we're very careful, or we try to be careful not to let the user just, willy-nilly go in and just start doing whatever they want to the internal workings. The user shouldn't even, whether it's your code or someone else's code, the client code shouldn't even have to worry about, how is this implemented as they're using it. They're programming to an interface, not an implementation. That's actually a software design principle called the, what's it called? The reverse, it's gonna drive me crazy. 1 second. Program to an interface, not an implementation. What is this? There's a name for this thing. Blah, 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 blah. I guess not. Maybe there's not a special name for it. I thought there was. So it's it's something else. Okay, so that's it's a really good habit to get it used to, is even if you don't have a language that actually supports actual interfaces like Java does, like C++ doesn't, but you should program based on using the API that's exposed to you, whether you're the developer of that or not, rather than trying to worry about the underlying workings or implementation all the time. And this get reference to is actually part of the underlying workings and implementation. So we don't want to really know anything about it. We don't want to expose it to the client. Okay, so public void clear. This one's real easy. While we're not empty, just keep calling remove, and it'll just keep removing the first element. So that version of remove just always removes the first element, right? So it's just going to keep going. And then when this is empty, the while loop will break, the clear method will be done, and the people will rejoice. Here's a class node that has set and get methods. Get data, set data, get next node. So this would be one that you wouldn't even necessarily need to be an inner class, or if you just wanted to make it look a little bit more appropriate in an object-oriented fashion. The thing that sometimes bothers people is that if you have an inner class like node inside of a bigger class like linked bag can access any of the private data inside of node because it's considered part of its internals as well. So it's kind of like human has access to their lung, and lung has access to the bronchioles. So human has access to the bronchioles, even though they're considered private or inner parts of the lung. Not that you should be poking your lung or anything. That's not a good idea. So this one just exposes a more object-oriented way of doing things. Now, let me see here. What else? Class within the package. Okay, this is if they made the class not private, but they put the class just in the package. So package access is if you don't specify otherwise. And if it's in the same package as the link chain, the link chain can then access this class. But at that point, the problem would be what? It can't access the private data anymore because it's not an inner class. So it would have to rely on things like get data, set data, and get next node, set next node, things like that. Okay, I think that's good for that. So pros of using a chain, just like we talked about with the array-based implementation, we're going to talk about it, pros and cons with the chain-based implementation. So a bag can grow and shrink in size as necessary. So that's a pro of using the chain, right? You don't have to allocate, say, 100 cells and then find out you're only going to end up using 50. Okay. Or if you have a dynamic array, you get to 100, you fill it up, and then it doubles the size to 200, but hey, you only needed 2 more cells. So you're wasting 98 cells. So in that respect, it actually saves memory. Remove and recycle nodes that are no longer needed. So that's good. They're kind of immediately returned, whereas memory you're not using in an array is just being not occupied or not at least acknowledged, but it's still taking up memory. Adding new entries to the end of the array or to a beginning of the chain are both relatively simple. Notice that that's kind of backwards for these. with the array, because of random access and because it's contiguous memory, we can jump to the end very, very easily and add a brand new item, assuming we have room. With a chain though, if we're going to point to the front of the chain, it's very, very easy to add to the front of the chain. And they're both similar for removal. So the array and the chain are both similar with removal. What are some cons? So removing a specific entry requires searching of array or chain. So that happens in both situations. A chain requires more memory than an array of same length. Why would you think that's the case? Because I said there is kind of a memory savings in this respect, because the bag can grow and shrink as needed. It only grows and shrinks by one node at a time. And it doesn't have any of the interference problems that arrays could have with other memory. But why do you think a chain with 10 elements, or okay, let's say 100 elements, why do you think a chain with 100 elements takes up more memory on average than an array of 100 elements trying to hold the same data, same type of data? Michael, yes.
Is it because for the chain, like when you move through a chain, you need to go through each thing, whereas like in an array, you can go like to the immediate thing?
Well, that has to do with jumping around elements, and that's also an advantage we have of arrays and not on chains. But that's not a memory issue; that's a processor issue or a time issue, right? So we've got two resources we have in computer science, basically. We've got memory, which is storage in memory, and we've got processing power, which is kind of like it ends up taking time. So time isn't really the consideration here as much as memory. So why does it take up more memory? Tom?
Just thinking about the nature of an array versus, this chain. The chain is scattered throughout the memory. So each piece of it needs to point to the other piece, or you'll never find it.
Right. So
so it just, in each piece, it needs to contain the additional pointing to the next thing.
Right. So that's extra data. Emma, did you have a comment?
Just what he said, like
Okay.
You need two things. You need the reference to the item in the list itself and the
Yes.
reference to the next element.
Right. Excellent. Yeah. So what happens in these nodes, if I have data, let's say I have data that I'm trying to hold, and I'm trying to hold the number 15, right? So if I had an array and there was a cell, there's a bunch of other cells down here, and this just happens to have a 15 in it also. Notice that for each element in the array, we're only holding the data. Okay, let's say that it could be an address too. Okay, so this could be pointing to some item down here. We'll just assume this is, let's actually change it so it doesn't get too confusing here, because that arrays can hold primitives, but we've been talking mostly about references, so we're going to go with that. Okay, and then we'll do that. So let's say they're each pointing to some piece of data in their respective environments with the same address or whatever. But you'll notice that to keep track of the data, the array just has all this contiguous data, and it only has each cell or each item you add only has to worry about the actual thing you're trying to focus on. But the node itself has to not only hold the data, but it also has to hold another address to point to the next node. So this is actually, if we assume in a non-compression, no tricks up your sleeve situation, this cell would hold an address. This would be 8 bytes on a 64-bit system, because that's 64 bits. And then this one would have 16 bytes or 128 bits just for a single node. So it's actually double the amount per node, but maybe you're saving on stuff because you don't have those extra, 100 elements you're trying to point to with the array. So there's always give and take. Remember, nothing's, one of the things I always try to stress to all my students in all my classes, that nothing is free. Okay, it doesn't matter who says something's free, nothing's free. And same thing in computer science, is that something somewhere is paying for this. Okay, there's always a give and take, and there's always trade-offs. It's very rare for someone to find an advantage without a trade-off. When they do, it ends up being usually pretty revolutionary, especially in large-scale systems. Are there any questions about this topic before we kind of we'll take a break and then we'll come back and we'll talk about the Big O notation. I didn't like their slides on Big O, so I decided we would use the supplement that I made, and we'll talk about it here. Any questions on this material so far? So we've talked about the bag implementation, the bag as an ADT. Before we worried about implementation, we said, what does the bag do and what's it supposed to remember and all this stuff. But we then talked about an array-based implementation of the bag. And now we just finished a link chain-based implementation of the bag. So arrays, most of the people who've taken any kind of Java or C++ or whatever, they probably are familiar with it by this point. But not all of them are going to be familiar with the chain-based implementation. And this is one of the major points at which you are advancing to a new level of understanding in computer science, or maybe you'd heard the terms before but didn't fully understand how they worked or whatever. So hopefully this is helping broaden your horizon, that there's multiple options for implementations, right? Okay. Any questions before we're going to call it a break for a little bit, and then we're going to come back and talk about the supplements. Let me see, where did my supplemental stuff go? There it is. Okay. So this is the, wait, did I? Link chain inventory list notes. You know what? I think I'm going to upload that just to help you guys. Give me 1 second. Since we covered it kind of heavy this week, I'm actually going to kind of repost the topic a little bit. Let me see here. Practical example. I'm going to copy that, and we are going to put it in Wink 4 just so you have immediate access to it and don't have to go fishing for it. So this is a link chain overview tutorial. Okay, so that's that. And then I'm going to also, I just want to make sure I'm looking at my information correctly. Quantity, quality. Okay, yeah. All right, so I'm also going to upload the notes, which also contains kind of a lot of code also. I'll upload that to this week, so it'll help you. All right. Okay, so we'll take let's say about a 15-ish minute break. So let's see, 26, 27. We'll say, let's just say 7:27. I'll put it in the chat. Come back at 7:27, and then we'll finish. We'll work on the Big O and asymptotic analysis. Okay, so we might use a little bit of what they say in the slides, but I like my stuff better, I think. So, okay, all right. See you in just a little bit. Take a break. Hope everyone had a refreshing nap. Now, we will move on to the efficiency of algorithms. We will use the first few slides here at least. This is actually a very short set of slides here. Some of it more useful than others. I really like my summary, so I would recommend highly that you kind of go through this, but we'll do some examples ourselves, just to make sure we kind of understand where we're going. And we will then just call it a day after that. So efficiency of algorithms, this is actually a huge area of discussion. Just making sure you guys can hear me now, yes?
Yes.
Awesome. Okay, so I did that once with my mic all the way on mute, and I wasn't watching it usually gives me like signals and stuff, but I was not watching, and I did that once. So that was about 5 minutes of my life I can't get back. Okay, so efficiency of algorithms. So we're interested in, are algorithms efficient? This is a very, very interesting topic to come up, and it was actually a really good segue because one of you had mentioned when we were discussing the situation with the memory occupied by nodes, one of you had said, well, you have to kind of walk through the chain and stuff. Well, that actually is very interesting. You were kind of ahead of your time, whether you were trying to be or not. We actually are going to talk about those two things here and kind of distinguish between them. So memory is one of our resources, and also, and we want to use it efficiently, and also the CPU or processing power. It could also be GPU or any other kind of processor as well. But processing power is another thing that we want to preserve and try to be efficient with. Generally, we're going to focus on processing power, meaning time rather than storage efficiency, which is like memory. Space. Okay, so we've got literally space and time. Kind of like physics, kind of different. Some similar concepts. Okay, so why do we want efficient code? Computers are already faster and have larger memories than they did way back in the day. In fact, we've come quite a long way. If we look at, I believe I'd mentioned this before, if we have the 1970s hard drive, which I believe I showed you all before, but this really gives us kind of an idea, really good idea, if I can find this thing. Okay, yeah, in the state-of-the-art 1970s, 250 megabyte hard disk from 1979. This is a form of storage. It's not main memory, but it's this is the best they could do with long-term storage. Okay, so I mean, these are you know, even having a small 250 megabyte hard disk. Gosh, I'm trying to even think of my maybe my Mac, it's very embarrassing, but the first computer I actually personally owned was actually a Mac. It was a Performa PC from like the early 90s. But it had like a 250 megabyte hard drive. Actually, in a matter of 12 years, we were able to go at minimum from something like this down to something the size of the guy's like front part of his foot. Okay, so I mean that's quite an accomplishment. And then past then, it got more and more and more impressive, right? So these are just different technologies and stuff. The one looked like they were making a Jello mold, but I'm pretty sure it was a hard drive. Okay, so these computers though have faster and larger memory, so that was storage, but we also have faster and larger actual memory we can deal with. Are we even worried about efficient code? It says they are faster, so that means we have faster processors now, GPUs and CPUs. So why do we really care ever? Why do we care ever about writing really super efficient code to try to make good use of it? And also, how do we measure efficiency? Because if we're going to talk about something like this, You know, some disciplines are better with dealing with arbitrary ideas and things like that. And when you're in a STEM area, science, technology, engineering, math, we're not as good with arbitrary you know, what we would call quality-based standards, as far as or what would you call it? We're more concerned with quantities and being able to quantify something rather than just qualify something, I guess would be the way to, we are obviously concerned with quality, but it means something different to us than it does, say, an art major or something like that. So how do we measure efficiency? We want something that's at least reasonable to measure efficiency. So consider the problem of summing. So this gives the mathematical definition. What is a sum? Okay. So if we have the mathematical definition of what is a sum up here, we sum from 1 to n, k equals 1 plus 2 plus 3 all the way up to n. And there are 3 algorithms listed here to do it. Okay. We have the standard technique that I think most people would probably use if they were just asked to do this. Even if they're very early programmers, you may not know any shortcuts that exist. So you'd probably have a loop, and you'd start from 1 to n, and then you'd say sum equals sum plus 1 plus I. And you just keep going, and that would take up a certain amount of time. Algorithm B, this is really kind of scary looking, because why are they using 2 loops? Well, what they're doing is each iteration of the outer loop, they're adding 1 to the sum however many times they need to. So if I say I'm at step 1, it's only going to go loop 1. If I'm at 2, it's going to go 1, 2. For 3, it's going to go 1, 2, 3. And you might think, why would anyone write code like that? People don't usually. They would probably, this would be the most straightforward one based on what we see here. But there's also a third algorithm. Okay, so I think what I'm going to do is I'm going to start Apache NetBeans real quick, and we're going to actually implement all 3 of these. And we're going to try to get an idea of what do we expect. Okay, so Java with Ant. Let me see, how did I name these things? I always forget. So we'll say it's week 4, right? So week 4. So week 4. Did I put CIS in front of it or after? I keep forgetting. Let's double check here. Okay, CIS 23. Okay, CIS 2353 week 4. We'll say algorithm efficiency. Okay, I will uncheck the create main class, make sure it's in a good directory of its own. And we have this new project here. I'm going to create a file. This one's going to be summation tests. Okay, so we've got our main function here in main, and we're going to have algorithm 1, algorithm 2, and algorithm 3. I think did they call them ABC maybe? ABC, we'll go with ABC. We'll go with their naming convention just to stay consistent. Okay, so A says we initialize sum equal to 0, and we go from 1 to n, and then we add I to that sum. So I'll start there. Public static, and then this one's going to, we're going to deal with integers, so we'll say int. This one's going to be called sum A, and it's going to take an integer. You know what, actually, let's return a, no, I guess I think that's okay. I'm trying to think, is that going to be good enough? For let's make it long just to be safe. So we'll say long sum A, and we'll say long n. And then all we're going to do here is we'll say long sum equals 0 for int I equals 1, I less than or equal to n, I plus plus, and then I'm going to say sum plus equals I, right? Is that what they did over here? That's what they did over here, right? Sum equals sum plus I, that's sum plus equals I, right? From 1 to n inclusive. So then we're of course going to return the sum that we've been calculating. So that's algorithm A. That's kind of the standard one that you'd probably fix or you know what, actually, let's see here. This probably should be a long also because it could get arbitrarily large. So we want it to be large enough. But this is what you would probably write in order to solve this problem. Okay. I don't know why I said fix. I think I said fix. That was weird. Okay. Now, algorithm B is kind of the weird one. So this one is saying we set the sum to 0, and then we go from I to N, just like we did it with the other one. So let's kind of start it like the other one. So public static long sum B. And then we're going to say long, I'll go down a little bit here, long sum equals 0. And then for long I equals 1, I less than or equal to N, I plus plus. And then this is where it changes though. Instead of immediately adding I to it, we're actually going to do a loop go up to I using J. So it's a inner loop. J equals I up to N, and then only add 1 onto it at a time. So it's going to give you the same result, but it's just this one's purposely going, it's worse. Okay. So let me see here, in 4, and then we return sum eventually anyway. We'll do the same thing here. So this one has the inner loop, long J, starting from 1 up to I inclusive. So we'll say 1, J less than or equal to I, J plus plus, right? And then sum, well, sum plus plus, okay? It could also be sum plus equals 1 or sum equals sum plus 1. Any of these would work, right? Because it's only adding 1 each time. The third algorithm, which has a name, actually, it's called Gauss's algorithm. Okay, Gaussian summation, public static long. Did I do long on this one? Yes. Public static long sum C, not pubic. We definitely don't need pubic. Okay, so we've got public static long sum C. Oh, that's nice. Home keys, guys. Everyone stay in your home keys. Okay, long N and sum C. And sum B, and then we'll kind of clean it up here, and sum A. There we go. So what do we do here? This one, we'll assume we're kind of setting it up the same way as the others. So I'll just write it out like this, even though we're actually adding kind of a step we don't really need, but it's not going to really affect it. The algorithm that we're going to use is actually just this straightforward little method here, N times the quantity N plus 1 over 2. So we're going to say sum equals N times the quantity N plus 1, and all of that over 2, right? So I guess that part doesn't really matter. I'm trying to think. No, it should matter, but we'll keep it like this because that's kind of how it's defined. All right, so these all should give us the same answer. So let's just do a couple brief sanity check tests. We'll say final long up to, and we'll say, or no, we'll just call it N, that probably makes more sense. Let's say 10, and I'm going to print out, not see out. What language am I using this week? Okay, so sum A algorithm is sum A of N, right? And then I have the sum B algorithm, sum B, and then sum C algorithm, sum C, okay? This is just our sanity check to make sure we're getting the same answers and didn't goof anywhere. Okay, so let's run this. They should all be the same. Usually gives it a little bit. Okay, yeah, 55. Let's increase it just slightly to say 15, just to give it another run and test it. I think we're good. Yeah, 120. Okay, so we're good. Now, what I'm going to add to this is something you may not have seen before, but we're going to kind of play around with this. We're going to say, let me say elapsed. Elapsed? That doesn't seem right. It should be 1L, right? Let me double check. It seems like it should be 1L. Elapsed. Elapsed. Yeah, it's 1L. Okay. That's what I thought. I was thinking of ellipse, I think. Okay, so elapsed, we're going to set to 0. We're going to say start, just to start these things, and then end equals 0. These are start and end time, and then the elapsed time. So we're going to actually time each of these using actual Java code. So the way I'm going to do that is at the beginning of this one, I'm going to set start equal to system dot nanotime. So that gets a number of nanoseconds on the system, and then end equals system dot nanotime. Okay. I'm going to say that the elapsed, you know what, just no, I like my idea better. Okay, so elapsed is going to be end minus start. And then I'm basically going to do kind of the same thing for each of these. I'm going to put a test for this one, system dot nanotime there. So it's going to tell you what time is it using the system in billionths of a second. Before it starts, it'll run its code, and then it'll tell you what it is after, and then you take the difference, you know how much time elapsed. Okay, and they're all going to be fairly consistent with the actual method call and the fact that we had to call a print line on each of them. So none of that's going to really affect it that much. So, but this should give us an idea. Okay, so end minus start. Same thing here, start equals system nanotime, and then get the elapsed time, and we're going to print all of these after each one. So I'm going to say well, here, let's do a tab. We'll say A took, and then we'll say elapsed nanoseconds, like that. And I'm going to copy that guy, put him down here, and just change the wording. So it says B. And then down here, same thing here, and just change this so it says C. Okay, so not too bad. We've got our 3 different algorithms, A, B, and C. So test algorithm A, and then we've got the test for algorithm B, right? And then the test for algorithm C. Okay. So let's run this. So we've got it with n equals 15. We're going to start it and see what the different results are. Okay. So here, at this point, we're getting that the first one, which is the kind of the more standard one, in this case, it's actually taking quite a few number of nanoseconds. Let's run it again just to see if that's consistent. And it does seem to be at this point. You would think B would be less efficient than this one, right? However, we're doing it for a really small number, so maybe there's a reason behind that. But you'll notice that this one down here, it takes 86,500 nanoseconds, so 86.5 microseconds, right? And then this one's 152 microseconds, 0.7 microseconds. This one's 523. I'm sorry. This one's, oh, this is 5 million. Okay, so this one is 5.2, 5,239 microseconds. So it's 5.2 milliseconds, right? So let's actually increase the number of n to 50. We'll say it's 50. All right, save that, run it again. Okay, not too much different so far. Let's try 100. Okay. All right, so let's make sure I got these right. Did I get right A correct? Yeah, I did. Okay. So let's see, right to n, I plus I. Okay, good. All right, so they all get the same result. Let's try bump it up to 1,000. Okay. Now you'll notice some of these are actually starting to kind of, get close again. But you notice this one's really not too bad. right? So this one's, 3.07 million. So we've got 3 milliseconds, 5.2 milliseconds. This one hasn't even gotten, this one's at 104 microseconds. Okay, so it's not even, it's at 0.1 milliseconds so far. Let's set it up to 5,000 and see what happens. Okay, now at some point, this broke the boundaries here. So this one is actually smaller than the second one, which is the second one. If you look at it, it's actually doing more work. So at some point, what's being done at the hardware exceeded what's being done at software. Well, I have to mute my microphone so I can cough aggressively. I just figured that'd be rude to do in all of your ears, because I still have kind of a lingering cough from my cold I had over the weekend. Okay, so this right here is 6 milliseconds. This one right here actually got all the way to 7.2 milliseconds. So that's pretty impressive. This one has not even gotten this one actually is less than the last one, which is kind of unusual, but it does happen sometimes. This one's actually at 88 microseconds, or 0.08 milliseconds. Okay, so this one's still really fast. They're all getting the same answer. So they're performing essentially, or they're solving the same problem, right? What if we have 10,000? By the way, in Java, you may not know this, but you could do that if you need to do a separator or you want to. Most people don't, but this is, especially if you have a lot of zeros, it makes it easier to see. So I put an underscore. Okay, now you should really see a difference. You can see that this one is at 6.2, approximately 6.2 microseconds. This one is at 16.8 microseconds, and then this one's at 0.1 microsecond. Okay, so it's getting bigger and bigger here. Let's do 25,000. So we're summing up the numbers 0 or 1 to 25,000. So in this case, this one actually went down, which is, could be based on background processes and stuff, but you'll see this right here. I've gotten up to 960 milliseconds. So this one's almost taking a full second to do this summation. And let's do 50,000. Did you see the pause that time? Everyone see the pause that time? Let's do it again. That second algorithm is really showing its weight. In fact, since this is getting like this, I'm actually going to put them in a different order. So I'm going to actually grab algorithm C, and I'm going to put it at the top because theoretically it should be the fastest one. So, but we'll get the solutions all, in their correct order. So algorithm C, oh, we have an issue here. Let me see. Okay. Yeah, I'm not sure why is C taking, oh, C must be taking the brunt of the setup or something. That's weird. Huh, strange. Okay, so you'll notice though that B is extremely slow, right? So this one's getting really, really bad. Let's put it at 100,000. Okay. Yeah, I'm not sure why this one's doing that. That's really weird. So it's I think it's actually going so fast that the start is actually getting called too late. But let me here. It seems like it arranges it properly, and it seems to get better numbers if we put it in the ACB order. That happened once before, and I never did look into it. So, but that's my guess. I think it's actually, unfortunately, it's counting some of the other setup stuff. And the first time it calls a particular function, it takes longer. So that does happen. Okay. Right. So I can keep doing this. Let me see if we go to 200,000. Watch that algorithm B at the bottom. Okay. Okay. This is pretty fast hardware that I've got here. Okay. But it doesn't matter if you have a supercomputer. If you keep taxing it like that and you keep using bad algorithms. So let's say I went to 400,000. So I guess that, hey, we have advanced hardware now doesn't seem to be doing the trick when you have a bad algorithm, right? Now note, you know, this is performing stuff at, you know, several billion operations per second. Okay. So the fact that it took that long, that one took 23 seconds in order to calculate the exact same solution that the other two did, is pretty telling. Okay. You know what? I'm going to do something real quick just to do a test. System nanotime. Maybe the first call to it actually takes up more time to, might not be getting the right value. That seems to have improved a little bit. Maybe that might have been what it was. But anyway, it's taking almost half a minute now just to process 400,000 elements. Now you might think, okay, well, that's a huge number of elements. Well, not really. In the grand scheme of things, we might be processing 1 million elements. This thing's going to take several minutes, if not longer, if we go up into the millions, because it's growing quadratically with respect to n. It's just too many. It's just way too much time. So this took 24 seconds that time. Yay, got more efficient. Okay, but it's a bad algorithm. Okay. So hopefully that demonstrates in practicality that these algorithms are all not the same. What do you think was maybe some of the problems with me implementing those? Like, what do you think might have been some of the general issues with comparing these algorithms by what I just did, by implementing them all like that? Tom, did you have a, yeah, Tom?
Well, just looking at it on the surface, C has one variable and the others have, you know, 3 or 4.
Right. Yeah, that's a definite,
which all need space and all need to be operated on.
Right. Do you think if algorithm C had more variables, that would be the major impetus? Or do you think it has something to do with the loops?
I mean, C also has the advantage of it's performing the operation right in the variable.
Right. So it doesn't,
and no
not
loops.
using, yeah, no loops. Loops take time, right? Because it's got to go duh, 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 right? This one's all one calculation, basically, or a couple calculations. It does one calculation, 2 calculations, 3 calculations, and then a 4th for the assignment operator. So it's a constant. It doesn't matter if n is 100,000 or 500,000, right? Tom, did you have another comment or?
No, sorry.
That's okay. No, it's fine. Okay, so yeah, so this would be similar to the code we just wrote here. So what does best mean when we're talking about algorithms? So an algorithm has both time and space constraints, time complexity and space constraint complexity, and that's called the analysis of algorithms. So I'm going to ask the question: do we have a better tool? Or okay, I guess I could back up a little bit. Got a little ahead. So we never did actually answer the question: what was maybe the problem with me going through and implementing these to do the comparisons? Now, at some point, let's say you narrow it down to several algorithms that look similar, it might make a lot of sense to maybe go through and do a kind of a preliminary implementation. But I just spent a lot of time trying to solve the same problem with 3 different methods, right? 3 different algorithms. And the question would be, is there any more rigorous way than, hey, that looks better or looks shorter? Is there a slightly more rigorous way for us to look at it and say, well, for at least larger numbers of n, as n approaches infinity or n gets bigger, at least, is there any way for me to know which one of these algorithms is inherently better or faster than the others without running it on a machine? So I just potentially wasted time implementing to do what we call a runtime analysis, where you actually run the code. had to, besides writing it, I had to actually run it and actually, you know, look out how many seconds it took and everything like that. So I had to do, you know, formal or at least semi-formal testing on it. And there may be like some of this stuff, if I were to just be given these options, even if I didn't know if this thing, you know, that might look a little squirrely, I don't know if it's giving the right answer, maybe we should test it. I could at least eliminate this one because it looks like it's doing so much extra work. So for every iteration of the outer loop, just like this one has an outer loop, quote unquote, I to N, from 1 to N, it's doing an inner loop from 1 to I. Okay, it's doing a whole lot more work. So I could have looked at all three of these and said, well, this one's clearly going to be the weakest link here. So why do I even implement it? Now I did it to show you all what was going on. And so we could actually kind of see it in action of what's called a runtime analysis where we actually run it. But this does not mean that we have to go through that process every time we have alternative solutions. So how do we define best? And we're talking about time and space. So we were just concerned with time because we were timing it. We didn't really think about memory, although memory, they can affect each other, but often there's even a trade-off. Like you might choose to take up a little more memory to save some time or vice versa. So counting basics. This is actually part of kind of counting theory and algebra, a basic operation of an algorithm. So there's this thing, it's kind of a little bit ambiguous, but it's called a basic operation. And we generally consider them things like additions, multiplications, divisions, even like comparisons. Like if we do if A greater than X, the greater than would be a basic operation. If these are the most significant contributors to its total time requirement. So with algorithm A, we had n additions going on because we had to go through that loop, right? And we had to add up stuff n times. So that's what we got, was an n down here. Algorithm B, for every n outer loops, the inner one we actually summed up the number using single ones. So they actually end up with this whole mess here. So we have n squared plus n over 2. And then algorithm C did what? It had 3 steps, arguably 4 if we're going to count assignment operations, but it's a constant. It doesn't, do you see n over here anywhere? Only on these two. So this one actually does not depend on it really. So I could look right away and say, in most circumstances, this one's going to be really bad because it's quadratic. It's got a quadratic term. This one's going to be linear with respect to n. So it's a little bit, it's going to be definitely faster than the middle one at some level. And then this one that is a constant, that one's definitely going to win, right? So this is their gross. Algorithm C stays flat. Algorithm A is the linear one. It grows linear with respect to the number of basic operations. And then we have as time goes on. So as time goes on, how many basic operations does it have to perform? For algorithm B, this one's actually growing like a parabola, right? So it's quadratic with respect to n. It's got a linear term in it, but which one's taking up or causing it to grow the quickest? Is it the quadratic or the linear term?
It's the quadratic.
Mm-hmm. Yeah, so always the higher term is going to cause it in general at some point, even if it was n squared plus 10n divided by 2, 10n would dominate it for a little while, but then eventually the quadratic term, as n keeps getting bigger and bigger, the quadratic term is always going to win out. So here, again, giving us an idea of counting basic operations, these are typical growth rate functions evaluated at increasing values of n. So here's our n value over here, and here are our typical growth rate functions. By growth rate function, we are talking about the number of basic operations that are performed over time. So that's what all these numbers are in here relative to the efficiency of the algorithm. So the algorithms we just saw, there was a linear one, there's a constant one, which we don't even see on here. That would be like 3 or 5 or 6. These only start at linear, but this one's linear and this one's quadratic, right? But there's also could be cubic, there could be exponential, there could be factorial algorithms. Those are very rare. Exponential aren't as rare as you'd hope. Log squared n is over here. Log of n is right here. Log of n, which are just called logarithmic, are pretty common. N log n is pretty common. This is called linear logarithmic. This is just linear logarithmic, quadratic, cubic, exponential, and that would end up being factorial. But look at how different these things grow. If you have an algorithm that's even log of n, the log of n is extremely rare. So we'll just go with log of n. If you have a log of n, even if your input is 1 million, it only takes like 20 basic operations. Okay. If you start with 10, it's only going to take 3. The log squared of n would take 11, so a little bit more. Linear would be 10. N log n, 33. So it's a little bit more, but it's not crazy. But notice how much bigger n squared is, even just for this 10 size 10 input. N log n, if you can have an algorithm that's n log n instead of a quadratic, it would be really nice if we could do that, because this is 33 and that's 100. But look here, if we just go to 100 input, this one ends up being n log n is 664. It's quite a bit more than 33, but look at what happened to the quadratic term. Okay, it's no longer 100. You know, it's 10,000, right? So it grew way bigger. Okay, orders of magnitude, it's growing way more. And that's one of the reasons the linear, even the linear versus the quadratic was quite faster when we were doing the different algorithms, because we had one with one internal loop that would actually operate in linear time. We had the one that had the 2 internal loops. So for every n, you could go up to the current n value, even though we were using I. It would have been slightly less than this by proportion, but it's still, you know, this is growing a lot faster than this one even, right? So you might think like, well, how would a logarithm get introduced into this, and what does that even mean? If you remember, a logarithm is kind of the opposite of exponential. So exponential means for every 1 additional size of my input, so if I went from 10 to 11, it would actually double the size of the number of basic operations it would have to perform. So that's really bad. We don't want an exponential algorithm if we can avoid them. So if I had 10, it's 10 cubed the number of operations. So that would be, you know, 1,000 basic operations it would have to perform just to process whatever these 10 elements are. If I added one more element, so I made it 11, it would turn this, it would double this. Okay, so that would be insane, right? So 10 cubed times 2 times 10 cubed. So that n doubles each time. So if this is 2 to the n, 10 cubed is 2 to the n, it would be 2 to the 10, 2 to the 11 is twice that. So that's insanely bad. Well, what about the logarithm? The logarithm does the opposite. The logarithm, you have to double the input size in order to make the logarithm go up by 1 more basic operation. So regular logarithm, sorry, this one right here. So you have to double the input size in order to go up by 1 more basic operation. So you will notice these are doing more than doubling. These are being multiplied by 10 each time, but this is still growing relatively, you know, small, right? So if we have 3 here, and that's log of n, log base, oh, the log bases are 2, by the way. In most of your math classes, you'll probably use base 10. But in computer science, log base 2 is the most common. All right. So it's to say it's opposite of this. But let's say we have 20 items to process, it would only take 4 basic operations. So doubling it. If I had 40, it would only take 5. If I had 80, it would take about 6. And that's why our 100 ends up being around 7. Okay. So some of these are growing massively. Some of these are numbers you would not be, you know, around for. Okay. So if I look at this and I say, we could write a program for it, of course, but let's say we'll say let's think here. Seconds to years. Okay. So if I have, I don't know if it'll let me do it in here, but we'll see what happens here. Let's say 10 to the 301 seconds. Yeah. Okay, so 10 to the 301 is 3 times 10 to the 293 years. Okay, congratulations. If you want to, cut that down by, maybe you have a really fast processor, you're still going to not be alive to see the result. Okay, let's kind of make it maybe a little more reasonable. Okay. Oh, this isn't nearly as bad. So this is 10 to the power 22 years. So if you have an exponential algorithm and you're trying to solve a problem that has 1,000 input, or no, I'm sorry, 100 input, it's going to take 10 to the 30 seconds, which is 10 to the 22 years. You might think, oh my God, it seems like there should be like more, more numbers down between the 30 and the 22. But the reality is, how many seconds are in a year? How many seconds in a year? Right? So it's got, 30 million, right? So it's not really that many in the grand scheme of things. So when you're talking about numbers this enormous, we're talking massive, okay? And you don't want a factorial algorithm at all, okay? Even on the smaller stuff, it's just really bad. So this one's gonna, okay, we'll say months on that one. Days, maybe. Okay, so it's gonna take over a day to process. If you have a factorial algorithm, it'll take over a day to process 10 elements. Okay, you might think, where do these freaking algorithms come from? And some of them are contrived just to show how bad things are sometimes, but some of them are like inherently like exponential, for example. So that becomes really, really bad. And we try to come up with alternatives and we try to find more efficient algorithms, but some algorithms, even if you're using a quadratic algorithm, which is way more efficient than a exponential algorithm, you're still going to end up in situations where these are just way too big. Okay. If you have a quadratic algorithm and, a million input like we have here, right? It's still it's going to take too long. It's just way too long. So if we can improve our algorithms or find a quicker algorithm in some cases, that really, really could help us. There are some people who are obsessed with matrix multiplication, and that seems kind of silly, but matrix multiplication really is kind of a fundamental component of being able to use and create really fast data science and AI processors. Or they use GPUs because GPUs are really good at matrix multiplication. Graphics processor units, instead of just a regular CPU, they have specialty hardware on the GPU to do matrix multiplication, because a lot of the stuff that goes on in video games and graphics requires matrices or uses matrices to like move the objects in the world and calculate where they're going next and do particle physics and all this other stuff. That's all using matrices. So you might think, well, what's the efficiency of a matrix multiplication? And a matrix, in case any of you forget what that means, because I know you don't necessarily take linear algebra, but if you do, I would say that's probably a good move. You've probably seen matrix multiplication like this, like that, and then we get the result. Since this is a 2 by 2 by a 2 by 2, the result's going to be 2 by 2. So we multiply this one by this one, and then this one by that one, and we add it. So 2 times 2 is 4, and then 1 times 1 is 1. So we end up with 5 in the first row, first column of the result. And then you do, the second column. If we want the second column's result, we do the first row, second column to get the first row, second column of the result. and you do 2 times 1 is 2, 1 times 2 is 2, and we add them, that's a 4, etc. Right? So that's a very simple 2 by 2. We're talking some of these, the dimensions on some of these matrices goes well into hundreds and stuff sometimes, and these are really, really hard to do sometimes. So that's the straightforward algorithm. The straightforward algorithm to multiply matrices is an n cubed algorithm, because it would require 3 loops. That's the one that's straightforward. There is one that's something like n to the 2.7 something. These are very rare numbers that we don't see in exponents very commonly, but this one actually was considered one of the only, I think it's 2.8, maybe it's 2.8, but it's even just the fact that it's improved is considered a really huge breakthrough on top of the standard form. But if anyone, it's believed by a lot of people that the actual, for practical use, there exists an algorithm that's a quadratic algorithm for multiplying matrices, but we haven't found it yet. But a lot of people see a lot of the different algorithms that they've tested. Some have gotten lower than this, but the problem is that they're smaller terms. I might have 2.8 or 2.5, we'll say, but let's say I have it plus 600 billion n to the 2 or something. It doesn't improve, so it's not practically usable. They're considered just stuff for theoretical mathematicians to play around with in their head, just to say, hey, the highest term is actually smaller, so that's an improvement. But in practicality, they're not usable. But if anyone can ever find a practical algorithm that is n squared, or even 2 to the 2 points, I don't know, 5 or 6, you'll be improving upon what we have now. Okay, so, and that could be a major game changer. So best, worst, and average case algorithms. So for some algorithms, execution time depends only on size of data set. Other algorithms depend on the nature of the data set itself. Here we seek to know best case, worst case, average case. And we use what's called Big O notation. So why are we doing this, or what is our goal? And our goal is to avoid having to, excuse me, implement all of the algorithms. Excuse me, wow. Implement all of the algorithms and do a runtime analysis, because it may not be feasible. So can we use math to our advantage to determine, hey, this looks like it's, at worst case, it's going to be such and such type of algorithm. So we do what's called Big O notation. Don't worry about this crap. I'll show you the good stuff in just a second. Oh yeah, growth rate. This kind of gives you an idea of growth rates of functions. If I have a growth rate and I'm processing a million items with my algorithm on a million operation per second, or it's a slow processor, but even if you increase it to 1 billion, you're not going to improve some of these very much, or 10 billion, it doesn't matter. But you'll see that a log-in algorithm, even on a really slow processor, 1 megahertz, is going to take far less than a second. N is going to take approximately 1 second. Okay. And what if it's the algorithm's n log n? You take that million, you end up with 19.9 seconds. As soon as you get to a quadratic, though, what happens? Now you're at 11.6 days just to process 1 million items, which is not extremely enormous in the grand scheme of computer science. We process stuff with billions of items sometimes. What about n cubed? Well, I hope you have a lot of time on your hands, because you're going to be waiting around for the solution for quite a while. I hope you checked your code really carefully, because you don't want to have to rerun that one. And then 2 to the n, you probably will be dead by the end of that, I would assume. Probably this one too, I would assume. Hopefully not the 11.6 days. But this one, 10 to the 10, a 1 followed by over 300,000 zeros, number of years. Yeah, no, thank you. Right? So, and then they kind of go over this, and they're kind of tactfully saying, what is the Big O of each of these algorithms we looked at? So add in the array and the linked base were both a constant. Because with the array, what do we have to do? Did it depend really on the size of the array? As long as we didn't have to resize and we had room left? No, we just kind of stuffed the item at the end using random access. And at the link chain, all we are doing with the bag is putting it right at the front. Did I have to walk the chain? In other words, did it have to do any kind of processing of n items in the chain? The answer is no. For remove, if it's the basic remove, it just removes the first element. If it's an item we have to find it. So you have to go through, at the worst case scenario, you go through the whole thing, right? So that's linear. And there's others too, like clear and get frequency contains and all this other stuff. And you might think, well, why doesn't it say stuff like, well, why wouldn't it be like 1/2 n? Because maybe on average, it's just 1/2 of the n. You never use constants, lower terms, or coefficients, except for one in the actual constant time algorithms. But for Big O, you never, you only refer to the highest term that was in your growth rate function. So even if it was n or 5n plus 600, we would only call it Big O of n. We wouldn't say Big O of 600n or 5n rather. And we wouldn't mention the smaller terms like 600, which would be a constant. So how do we do the calculations with this? Well, that's where I thought the book was a little bit weak, so I created this thing. Big O analysis, also called asymptotic analysis, because it says your code performs or creates an asymptote approaching another function. We refer to the book for a deeper discussion of the topic, so I'm just making that mention. These are the order of the most popular Big O's that we'll encounter, and probably in practical reality. We've got 1, 2, 3, 4, 5, 6, 7 of them, right? So, and they're in order of most efficient, which we would say is least complex, all the way up to the least efficient or most complex, meaning takes up way more basic operations and takes a lot more time or space, depending on the situation. So if we can get a constant algorithm, that's perfect, because it doesn't matter how big n gets, it's going to perform in approximately a constant fashion. Now, there's going to be, in practicality, there's going to be factors like how does the hardware work and what memory do you have available and what kind of speed is this and what does that do. But in general, we can look at these things mathematically and get a really good idea as to whether one thing is better than another in practice even. So logarithmic is the next step up. I know there was the log n. We don't see that very often, so I eliminated it. You're not gonna be responsible for that. Just these. N is linear. N log n is linear logarithmic. N squared is quadratic, like a for loop inside of a for loop, and both of them are potentially going up to n, each of them. Quadratic would be kind of the same thing, but you'd have those two inside of another loop going up to n. And then n 2 to the n, this is really bad, the exponential, you don't want that. And that's usually when the, it's usually a very, very difficult thing to process, and a lot of it ends up being something like, okay, some of the algorithms are in like graph theory and things like that. So if you had a node, and every time you add a new node, it has to rerun its algorithm, and it has to visit every other node in the graph and find the most efficient, route. So it may have to run it like several times to try to find it if you're going to do a brute force attack and things like that. This is actually one of the reasons cryptography works, is because often brute force attacks, meaning they're just going to start trying passwords or start trying to, attack the system. Often they have this kind of complexity to the problem without backdoor information, meaning if you don't have the password, you're going to have to keep checking. If you do have the password, it's usually pretty straightforward. So you could think each of these is a set of algorithms, not a single algorithm. So they're not a number. They're not each a number. They're just basically sets of algorithms. If we're looking at algorithms as kind of an entity that we want to discuss, that we want to be able to compare, we would say this algorithm goes in this set right here, This algorithm goes in that set, that algorithm goes in that set, this algorithm goes in that set, etc. And we'd like to compare them, then you can think of them as sets. That's probably a better way to do it. The value of n in the above categories represents the problem size, which is often the size of a collection, such as an array. So if you have 100 elements you're trying to process from an array, then the size of your problem is 100. Big O of 1 is constant time, suggests the time taken with a particular algorithm or algorithm is independent of the size of the problem. Now, that solution we had earlier was the Gaussian sum solution. You remember it was the n times n plus 1 all over 2, like that. So it was this algorithm right here, or that complexity rather, right there. And this thing, it doesn't matter how big these n's are that we're trying to process, it always does it. It can do it in one multiplication, or does the calculation in one addition, one multiplication, and one division. As kind of a side story, in case you're interested, how did anyone come up with this? An 8-year-old came up with it, but he was a very smart 8-year-old. And his name was Carl Gauss. He lived many, many years ago. And what happened is the teacher kind of came up with busy work for them. Stories vary. I've heard stories ranging from they were acting up, so she punished them, to she had a headache and a hangover, to everything. They were in Germany after all. So, tons of beer for breakfast type stuff. So if we have this and we're trying to add all the numbers, let's actually just start with, we'll do this because we'll just keep it kind of simple. He noticed when the teacher got fed up or whatever, just didn't want to teach, and said, I want you to add up all the numbers from 1 to 100. So all the students started. They were like, okay, 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10. Okay, wait a minute, we've got the 5, the 6, and the 7. Let's add those together and then add it to the 10. So they were doing it that way. Gauss looked at the problem and kind of thought about it for a minute and came up with something no one had noticed before. So we have the last 3 numbers and the first 3 numbers, just to observe. You'll notice that the 1 on the one end, the first number, and the very last number, if you add them, it's 101. If you come in 1 from this side and 1 from this side, it's 99 plus 2, which is also 101. You come in 1 more, it's 101, 98 plus 3, 97 plus 4, 96 plus 5. So he noticed that there were the numbers he was adding up to was 100, right? So he said it was 100. So there's this, but also what was the actual value he was getting? He was getting that 101 each time. So what he noticed is there were 50 pairs of these 101. So you got 50-50. And that was the solution. So he just very quickly solved this. The teacher was like astounded. No one had ever seen this before. And they came up with this new little thing. This is the generalization, but his was, of course, 100 times. It ended up being like something like this, divided by 2, right? So to figure out his 50-50 thing, he had this. Never underestimate a student not wanting to do more work than he has to. But Carl was kind of unique. He liked math a lot. But that's what we got. So, but it turned out that this works with any set of numbers you're trying to sum. Now, what is the implication for us? Do you think the processor has to do more work when it's just doing an additional multiplication and a division, or when it's doing a whole bunch of for loops? At some point, now the multiplication is kind of expensive at the hardware level, and so is division, relatively speaking, compared to with like an addition. That's why when we saw for really small sets of n, even for a human, if I asked you to add 1 and 2, the first 3 numbers, you're probably not going, or 4 numbers. Let's do 4 numbers because it's even. You're probably not going to go, okay, well, I need to take the 4 and the 1 and then the 3 and the 2 and add those and then divide that whole thing by 2. You're doing more work than you have to. Most people are just going to go, okay, that's 3, 6, 10, and they're done. So that's the same thing a computer can do, is it's just doing a few additions. That's cheaper than setting up the multiplication and all this stuff. However, once you get to a certain point of number of loops or inner loops and number of basic operations it's performing, that becomes way more expensive than just doing this thing. So he discovered that algorithm. Now, where do we find ourselves? The formal definition of Big O, which is our process of determining, it's our syntax for determining what a particular algorithm does and how efficient that algorithm is and how to compare them. We use this table, of course, but we have to be able to determine what is, what is it versus another, what's one algorithm versus another, and what does it fall into. And this may look looks a lot more complicated than it actually is. So we say that we don't say that a function f of n equals big O of n, although some books will actually write that. I'm not sure if the current book does. I don't remember, but it's actually mathematically not really accurate. We would say that it is big O of g of n, or you would say is order of g of n, if and only if the following holds. Now, what do we mean by this part? So if I have an algorithm with a growth rate, remember we were talking about growth rate functions? If I have an algorithm and I discovered that my algorithm is maybe 3n squared plus 2n. So it's got, maybe it has to go through 3 times, it has to go through a set of quadratic or double loops, and then maybe twice has to go through some linear stuff. Maybe that's the growth rate function of my algorithm. My question would be, what is the big O of it? What do you think intuitively the big O is of this? Looking at some of the options up here. You don't even have to be real good at articulating how you came up with the idea, but just because we're going to formalize it a little bit in just a minute. So what is the big O of this thing?
Quadratic.
It's quadratic. So you're saying it's n squared. Yes, the answer is correct. Yeah, because we can actually look at this and just see that's the largest term, right? We like that. Okay. Now, if it was something like 5n by itself, or 5n plus some constant like 100, I would say it's big O of n. So it's linear. We look for the largest term, even though that 100's going to kind of dominate the growth function for a while. Eventually, as n tends toward infinity, as it gets bigger and bigger and bigger, eventually this is going to be the term that dominates. So we would say that that is a linear algorithm. Okay. Now, how does this hold here? So we're saying if I have my, say, 5n plus 100, that's my f of n. What are the g of n? Or what's the g of n? The g of n are all of these. 1 log n, g of n equals n log n, g of n equals n squared, g of n equals n cubed, g of n equals 2 to the n. Okay, and they could be different, like they could be n to the 27. It doesn't really matter. It's just what is your g of n. And what the big O definition is, this is our definition. It says that f of n, our function, stays under or is less than or equal to. Our function sits under the other algorithm as long as you are able or allowed to multiply a constant by it for some n at some point that you pass, or as n gets past this n sub 0. Now, n sub 0 is the kind of the cutoff point. Like I said, if I have an algorithm that's 5n plus 100, the 100 dominates it for a while, but at some value of n, this f of n is going to be below this right here. It's going to be bounded by it and described by it, and it's never going to get higher than it again. Okay, so it is possible with some of these graphs that we'll see, you might have an algorithm, your algorithm might do this, and then this is the g of n. Okay, but this one's going to, at this point, something happens, and that's our n sub naught. That's basically at some point, this algorithm is going to overshadow yours as far as being less efficient, and yours is always going to stay under it. Or worst case scenario, it'll be identical with it, like it's going to overlap it, but it'll never go higher than it past that point. Like this is never going to like, oops, and do that. So they are actual functions, not, they don't behave randomly. So they're fairly well behaved. And the G of n will typically be or often be one of these categories in reality and practice. So don't get lost in the math and ease. All it says is your algorithm is represented by the function n, or f of n rather, and your algorithm is G of O of G of n is to say that if and only if it is bound from above by this constant C times G of n. An important role that is that we're not concerned with all values of n, just as n becomes large. There may be many values of n for which the inequality is not true. So this may not be true for all values. We're just saying when it gets past this point, it becomes true and it remains true. So practical questions are, we can look at these and say, what is the big O? And you might look at them and say, oh, okay, 3n squared plus 5n plus 7, that's got 3 different terms, but which one has the highest term or the largest degree? The n squared. So this one's a quadratic. What that means in practice is that the linear and the constant part aren't as important. Neither even is the coefficient. What matters is we're talking about this n squared. Definitely the linear and the constant don't matter. The coefficient is going to have an impact, but it still grows at a quadratic rate. Now, let me see, did I do an actual calculation for you? I think I did. Okay, so we'll actually, am I using the same values? I don't want to redo work. Okay, let's do this one. So let's say I have this one right here, okay? And I want to prove that it is big O of n squared. So I have a feeling that it is big O of n squared, that it doesn't grow any larger than some c times n squared, right? So would you agree that a 4n squared could probably handle this at some point, at some value of n? The 4n squared is going to grow faster than this whole thing, even with the linear and the constant contribution. So you could make that claim, but then you'd have to solve for what n do they cross at, basically. So I have a really kind of simple way to do this, and it works with pretty much all the any polynomial, and pretty much all the tests I'm going to ask you stuff on, it's going to be polynomial. So I call it the grouping technique, and it's the one I show you in the rest of that form. So I have this, right? So I'm claiming, or what I need to find in order to satisfy or prove this is an existential proof, meaning there's more than one solution. There's actually infinite number of solutions. You just have to find a value of c, and you also have to find a value of n naught. That should be like n sub 0, by the way, but I'll just put n 0, right? So I need to find AC and a matching n naught that make the inequality true. So what was the inequality? If we look at the definition of big O, what's our inequality? It says that the inequality, our function f of n, has to be less than or equal to c times some g of n for n greater than or equal to n naught. So I really need to find some constant that makes this true at a particular point. My promotion technique works this way. I leave my f of n and I go directly based on this description right here of big O. I leave the f of n on this side the same way it is. I say 3n squared plus 5n plus 7 less than or equal to, but then what I do is I put the same function on the right side, but with all of the terms promoted to the highest degree, okay? This isn't anything magical. It's just to make finding the n value, the n naught value simple, but you'll see why I'm doing this in a second. You might be like, well, why didn't you just pick 4n and go, or 4n squared and go from there? This is why. Okay, so I'm promoting all 3 of these, so 7n squared. So all of these are promoted to the highest term. Do you see what I did just then? Okay, I just promoted every term from the original to the highest term, the n squared. Okay, left the coefficients the same, promoted the ones that needed promoting. Now, I'm making the statement 3n squared plus 5n plus 7. That's my original f of n over here, less than or equal to, if I add all these, since I can combine like terms, I have 3 plus 5 plus 7, right? So it's 15. 15n squared. Okay, does that look like something we can work with? Because I want to prove that it's big O of n squared. So there's my g of n. Where's my c? It's something being multiplied by the n squared. Where's my c?
Isn't it the 15 in this
Yeah,
case?
absolutely. Yeah, so basically I've just solved that c equals 15. Now I have to find what's the correlating or corresponding n sub 0. Since this one has a constant on this side, I'm going to need to at least have a 1 on this side, but you can find that that's true. So n has to be at least 1. So the n naught is 1. And that makes this inequality true. You can actually test it. If I plug in the n naught as 1 and I calculate these things, 1 squared is just 1, 3 times the 1, and then you have a 5 times 1 here and a 7 by itself. 7 plus 3 plus 5 is 15. And then I'm asking, is 15 less than or equal to 15 times 1 squared? 15. So 15 is 15 less than or equal to 15? And the answer is yes. Of course it is. So that is one way. That is the promotion way is a really good way and a really quick way to come up with a proof. And remember, these are not unique numbers as far as the types of proofs you can do. It's a very easy proof because it's an existential proof. You just need to find an example. If you can show an example of where this is true, then it's generally sufficient. Okay. Some of these are kind of much more like robust, but let's see what happens if we do that one. Okay. Let me clear this. Does anyone need to take a screenshot or anything? I have answers to other ones down here, so it's not like you're being left, completely out in the open. So usually I'm going to give you your, I'm usually going to give you the function I want you to work with as T of n. So it'll be called like T of n. T of n is your f of n, by the way. If I call it S of n or T of n, don't be alarmed. That's just saying like space complexity or time complexity. That's why T is used a lot. So I'm going to say T of n is equal to, and let's use this third one here. So 15 n to the 10th plus n to the 5th plus 3n. I'm going to have to expand this a bit. 3n squared. And we're claiming, is it big O of n, big O of n to the power 10. Now, notice this isn't one of the common ones, but the end of the 10 is actually the fastest growing term. So we would pick that. We would say, oh, it's got to be big O of n to the 10. Now, that would be much more unusual in actual algorithms because, to get to that point, you'd have to have a whole lot of loops with loops inside and more loops, and it would be a lot of processing. But to do the calculations, this is how we would work with it. So again, we want to go directly off the definition. We want our f of n to be bounded on top by c times g of n for n greater than or equal to the n naught, right? So our f of n is our t of n. So we want this whole thing. I'm going to actually do a copy pasta because I don't like messing with this. So we want to find a c and we want to find an n naught. So I'm saying that that's less than or equal to, and I'm going to write it on the next. Well, actually, I'm not going to. I'm going to. Yeah, never mind. I'm lying all the way around. Okay, so I'm promoting all of these terms to the highest term. Then what does that mean I can do? I can combine like terms, 15 plus 1 plus 3. So that's 16 plus 3, 19, right? 19 n to the 10. That just saved me a whole lot of time because that's in the format I needed it. It's a c times g of n. It gives me my c. My c is 19. In this case, since I don't have any constant terms on the original on the original function, growth function, I can just say that it's going to be true greater than or equal to 0, right? Everyone happy? Sort of. Okay. So proving the big O of an algorithm, I've got 3 other examples in here, and I show you how to use my promotion technique even further, like on each of these, just so you can get more practice with it. And another, in addition to being given the T of n and being asked to find the big O and prove the big O, not just guess it, because all of us could guess it. It's easy. You look for the highest term. The other thing you might need to do is to be able to determine the big O from code. Now, this is not going to be identical the way that everyone does it, but if you do it at least reasonably, you're going to come up with a similar answer to what I come up with. Okay, because remember, we're talking about big O, not a real specific growth rate function that we need to be really, really super specific. So in this case, what I did is I was counting number of basic operations. Now you might look at this and say, I don't think that's a basic operation. Fine, don't count it. That's fine. And that might seem like really, really dirty since we're dealing with a lot of math here, but it is fine. Let's say for this, what I do is I count a declaration as one basic operation and then an assignment as one operation. So I actually give that 2 basic operations. You might decide, well, I just want to count this as 1 because there's not anything super complex going on. So I'll just count it as 1. That's fine too. But I just prefer my technique. The same thing with the int y equals 10. Same as above, we get 2 for that. Now the loop is where it changes. In the actual loop header, we have to pay attention to what's going on. So there is a declaration and an initialization that's only performed once, but it's the same thing as going on up here. So I counted that as 2 operations because it's an initialization or a declaration and initialization. Then I'm asking, how many times is I compared to n approximately or exactly? Well, if you're going from 0 up to 1 less than n, even if you shifted that over to 1 including n, it's happening n times, right? And then what about this? How many times is that called as you loop for the full life of the loop? And that happens n times also, right? So I found out that I have 2 from this declaration. I have n contributed from the middle expression there, and then n contributed from the increment operator at the end. So I have 2 plus 2n or 2n plus 2. So that's that contribution. What about inside the loop? This one I'm counting as 2 operations. I've got I already declared X earlier, so I don't have another declaration. But what I have here is I have an addition and an assignment. So I would count each one as 2. That's where I'm getting that 2 from. But how many times does it happen? You're in the loop, right? So it's going to go up to n times. So I consider that 2n. Outside the loop, let's say we just decide we're going to increment X for some reason. Maybe it's part of the equation or something that we're trying to calculate. But I just decided to do it. Well, it's not in the loop. So all we do is, and it's done 1 operation. You could argue that that's X equals X plus 1 and then get me and say, well, that's 2. Well, that's fine too. I chose to just consider it 1. So return X, we'll consider usually return statements, pretty much everyone would probably agree that's probably 1 operation. So what happens when you add up all of these things? Okay, you end up with 1 plus 2 plus 2 plus 2 plus n plus n, or sorry, 1 plus 2 plus 2 plus 2 plus 2n plus 2n plus 1 plus 1. Okay, because we have 2 n's rather. Combine all like terms, you get 4n plus 8. So guess what? That gives us our T of n. So sometimes I provide it for you and ask for the big O. And in this case, let's say you're not asked to prove it. You're just say, well, find the growth rate function and then say what big O you think it is. And you don't have to prove it. Then you just say, well, highest term is linear. So I'm going to say it's big O of n. And you're right. Now, if you got something a little bit off from mine, let's say you counted that as a 2. And let's say you counted all the declarations as 1s. or no, here, I'm gonna strap it down a little bit. So let's say all these are ones instead of twos. So I have 1 plus 1 plus 1 plus 1. So it's subtracting 1, 1, 1, and 1, 1, 1, 1, 1. So 4. So you'd end up with something like 4n plus 4. Who cares? That's still big O of n, right? So it seems haphazard, but it is formal enough that we can get something that gives us an answer about what kind of efficiency does this algorithm have. And I can look at this and say, oh, well, this method is linear with respect to n because of that. Okay. Then I give you another example. You can go over that on your own just to practice. You might not agree with all the numbers I put on the side, but if you end up with a completely different answer than I did, meaning you got a different big O, then there's a problem. Okay, that means you decided a single for loop ended up somehow as n cubed. And that's usually not the case. If you had I less than n cubed here, that would be the case because it would have to go n cubed time, and that is dependent on n. But that's very rare to happen here. I do have one little question for you. What if I had a loop? I'm going to give you a little bit of code here. Let's say I have a loop, int I equals 0, I less than 100, I plus plus. Okay, give me a second. Okay. And then let's say we, I don't know. Let's say we have some variable that we've already declared somewhere else here. Let's say this is basically the majority of our function, or at least everything we're going to know about it. And let's say we're finding the big O of this segment right here. That's fine. Okay. What is the big O of this segment? Okay, even without doing anything formally, just tell me what you think the big O is. Tom.
It's a constant.
Right. So that means why is it big O of we would say big O of 1, even though there's a bigger constant involved. Why do we do that and not say n? There's a loop here.
Because n never has any effect on what this does.
Correct.
It's just defined as 100.
Yes. So a lot of instructors, when they teach this, they automatically say, well, you can assume a loop is always, linear by itself. And then if it has another loop inside of it, that's quadratic. That's not always the case. That's only if it goes up to n. Okay, I have another one for you. Little more challenging. Excuse me. What's the big O? Any ideas? As a hint, if you need a hint, n divided by 2 is the same as 1/2 times n, right? So we'll say that. Did someone have an answer, or maybe I missed something? No? Emma?
Is it just n?
Yeah, why would you say that? You're correct. I'll tell you that part. I'll tell you that much.
Well, I almost get it, but I don't totally get it. But I think that's because you can multiply that by some bigger made up constant that would upper bound 1/2 times n.
That's a close way to think of it. Remember, when we're finding the big O and we get our T of n, let's say it's something like this, we ignore coefficients, right?
Right.
So as far as this is concerned, n divided by 100 and n divided by 2 and n, they're all the same because you ignore the coefficients. And this has a coefficient of 1/2. It's 1/2 n, right?
Right.
So that is big O of n. You're correct. Good.
And I guess when determining this, you just want to think of n as it goes to infinity.
Yes.
As it just gets really big. Okay.
Yeah, we are concerned about that, especially when you're doing comparisons about stuff, because we make kind of a bold claim when we talk about these the properties of these algorithms in these different classes or orders. And I would say, for example, pretty much I would say that the quadratic algorithms are, I can make a bold claim, algorithms that are n squared for large, you don't even have to specify that because it's implied by the definition of big O. You just say that n squared algorithms are more efficient than n algorithms, linear algorithms. Okay. Now, do you have to be careful in practice? Yes, because if I have mathematically, if I have one algorithm, we'll say it's a T of n number, T of n is, we'll say it's 2n squared. And then I have another that's like, we'll just say R of n, just to have two different variables here. And let's say this is 5,000 n plus 10,000. If I'm asking you, according to big O, what are the big O's of each of these? What is T of n's big O? Big O of what?
N squares.
N squared, yeah. What's the big O of R of n though?
N.
N. Okay, now if I told you that we were processing 10 elements, which algorithm would you pick? That we would never process more than 10 elements, but we need one of these algorithms.
Second.
Yeah. No, sorry. This one, I lied. So you would normally want to pick, you would normally pick the linear one, right? But these are so massive. Let's look at what would happen if I put a 10 in here. So if I have 2 times 10 squared, we get 200, right? Okay, so for n equals 10, we get 200 as the number of base operations, right? So that's our basic operations here, right? What about this one though? If I put 10 in here, I get 50,000 plus 10,000, that's 60,000 basic operations. So there does become a point where, you know, the theory seems to conflict with practice. But remember, the big O tells us that this depends on what n we're at. As n tends towards infinity, yes, we are going to eventually pick this linear one. But in practice, for these types of algorithms, this one's definitely going to suck up more time than performing this algorithm. So you do always have to consider practical implications, the fact that big O always is relative to large values of n. So at some point, this quadratic is going to overtake this linear. It's inevitable. But when that happens, now, are you normally going to get these types of coefficients, like 5,000 single loops versus 2 double loops or something, 2 nested loops? It's very doubtful. Okay, and then you have just 10,000. I mean, this is possible depending on how big your code is, but it's probably pretty rare you're going to have 5,000 loops in a particular segment of code. Yulia, yes.
So basically, we have to not worry about big O, but more about how many operations and how big numbers are.
In practice, you want to at least be careful. The big O is a guiding principle. And if I'm asking on a theoretical basis, big O gives us a great idea about how algorithms are going to perform in general. But when you actually go to implement something, if you know that there's like an enormous coefficient on one of these things, you do need to consider that before you go implementing it in practice. If you know, for example, you're only going to be processing up to 100 elements, and you've got this, you've got like an n squared, but then the other one's got like 100,000 n or something for whatever reason, you know that one's it's going to never within that range. The one with the lower term is actually going to always be larger, or frequently be larger than the one with the higher term, even though that kind of is counterintuitive from what we know from big O. So I'm just saying that as a warning and as a practical consideration, just make sure you pay attention to the numbers in here. But if I'm asking you on a test, what's the big O? Or even if you have a couple algorithms and you know for certain one of the algorithms is n squared, one's n cubed, and you're going to be dealing with large numbers, and there's not really a ton of coefficients or, maybe constants or something, then you would definitely go with the big O. Had to cough. All right. So does that help? So I would go over this extra sheet that I made here, this extra document here. The book has information in it and it has a deeper dive into some of the side topics, but I considered a lot of what they described as very verbose, and they went really, really mathy on some areas that are like even beyond what I'm doing here. And they also don't show you the promotion technique. If you don't like the promotion technique, you don't have to use it. You would just have to say, well, I'm gonna assume that 4n squared, maybe I'll pick 5 just because that's a nice, number, or 10. I'm gonna assume that's going to overtake this pithy little 3n squared thing. So I'll use 5n squared, but then you have to find what's the point at which there's an overtake, right? So you have to calculate, you have to solve for n basically. But if you use the promotion technique, it kind of saves you some time. Okay. Some of them you wouldn't have an option for, like logarithms and stuff. The promotion technique doesn't really work the same way. It doesn't work as well. So you'd have to calculate them anyway. But for stuff I'm going to actually test you on tests and stuff, as actual runtime analysis and giving you T of n's and things like that, I'm going to give you polynomials without logarithm being the highest term. We'll put it that way. Okay. Are there any questions about this? Any questions? No questions?
How many,
Whoa.
Sorry.
Yeah, Jamie.
How many questions would you expect to have on an exam? Related to
Off the top of my head, I don't recall. Some of them are pretty short, like they might be like 18 or 20, but some of them might be real simple, like a multiple choice. Some of them might involve you doing calculations or things like that. I issue them through D2L. And I use the D2L quiz software directly. So I do make ample use of multiple choice, but I also might have a couple that you have to actually kind of go through the process and, decide. Or I might even give you I might tell you, use the promotion technique, and you have to prove that you can come to an N and a C value, so something like that. Okay. Who the other gentleman that had a question? Yes.
I guess I was just trying to think of, for N naught, you're basically trying to find, I guess, the ceiling at which your function and the big O function intersect.
Yes, the point at which they intersect. So if you've got your function may vary. Your function might usually when we have this type of situation, your actual function might end up going one way, kind of going this curve, and then the other goes that curve. But at some point, even though your function might even start larger than the G of n, the C times G of n down here, right? Yours might start larger. It won't finish larger. So at some point, the idea is that the C times G of n is going to overtake yours, and it's always going to be bigger or more computationally complex than yours. So basically you're saying that yours is bound by that larger function. Another thing to note is technically, I could say, if I had this T of n, well, here, okay, we'll go to the T of n is 15n squared, blah, blah, blah. And we decided it was big O of n to the 10th. Well, since it's big O of n to the 10th, it's also big O of n to the 11th. It's also big O of n to the 12th. It's also big O of n to the 100th. It's also big O of n to the 20. The thing, what I'm saying there is that all of those would bound this function. But when I'm asking for it on tests, I'm asking for a more precise definition. Typically, although I'm not going to confuse you with the syntax, I might call it the big theta. That actually means it's more precise. It means don't go any bigger than you have to. But I'll just say big O. Okay.
So in practicality, this, if you have an idea of how many iterations your code has to run for whatever n is, this gives you a good idea of when your algorithm needs to be cut down or left as is.
It could. Sometimes you don't have the option. Like you may have the most efficient algorithm available or that anyone knows of. And that's where it gets a little tricky, because then you start like, it's actually a miracle in many ways that like Google Maps and software like that work the way they do, because finding reasonable paths, they actually use what are called optimization theory, or what's called optimization theory. If it was the brute force, the algorithm would be what we call intractable. So you try to get even down, I wouldn't say down the street, but let's say to the other side of town. You're in Detroit, or you're in Farmington Hills or Ann Arbor or what have you, and you're trying to get just to the other side of town. It's going to spend a tremendous amount of time figuring it out. Think of all these different intersections, and you want the most efficient path. It's going to really mess with itself trying to find out all the different possible paths to get from one place to another. Okay, but in some cases at the large scale, if you shortest path isn't really that difficult, but let's say you were trying to you had 5 or 10 or 20 different spots you wanted to hit, and you wanted to go the most efficient way. That would become an intractable problem. That's called the traveling salesman problem. But it would also be like if you're trying to, go and visit your family, and you want to come up with the most efficient, maybe plane route to visit family that live in different states, the most cost-effective plane route. That's actually considered a more of an exponential problem. So your GPS actually, your GPS maps and things like that usually settles for a good but potentially suboptimal solution. And the trade-off is that it's not going to take 15 years to try to calculate the route for you. So sometimes suboptimal is good enough. But that's like an advanced algorithms course. Okay, so I wouldn't worry too much about that. Any other questions? Emma, you had a question, I think, or maybe we answered it.
I'm gonna wait until my book arrives, and then maybe I'll ask you.
Okay, that's fine. That's fine. Okay, that's fine. Any other questions? No other questions? Okay, I'll hang out here for a few extra minutes if anyone has any kind of follow-up questions or anything. But you are dismissed. You're allowed to leave if you'd like. I will make sure that once this is saved, we can upload I'll upload it to YouTube under a private link and then or unlisted link, and then upload it. Next week, if all goes well, you should have your first programming assignment. All right, you're dismissed. I'll sit here and wait for a little bit.
Have a good week.
You too. Thank you. Yes, stay warm. You stay warm also, Yulia.